Roman DiBiase.
Joe Marie Del Vecchio.
Colin.
Jennifer Williams. Keaton Rogers. Natalie Carter.
Brandon Forsyth.
So Natalie is a postdoc working with my husband Andy Natalie, and Andy and I were trying to do a really dense seismic study in Shale, and she's going to be helping organize that, and that's happening in June. And we're going to need a lot of people to help with that, so we'll see stuff about that if you haven't seen it. Okay, so we're trying to expedite get this done fast today because today's Good Friday and Passover, which in some religions and for some people want to get out of here. So the 2018 data call is open, and we need you to submit your data sets. Have you gotten any?
Done.
Okay, so we usually start ramping up the pressure. What's happening? Our field cleanup is scheduled April 10th. It begins at 8:30 in Shale Hills. Anything else about that?
And if you guys can't make it, I know it's kind of a one last minute because of other scheduling changes and things that we wanted to do it earlier. So there's another report going the week after that. So if you can't make it that day, let me know for your group. Then we can schedule another day. Everybody's participated in some way.
Yeah, every group has to have somebody participate either on April 10 or through working with Brandon. It's the only way we get cleaned up. Every group participates. It's fun. April 19, Brian Swisstock, who's an extension, Penn State Extension agent, Water Resources Extension, he's hosting a group of Water Resources Extension educators here, and we're going to host them in the watershed from 8 to 12, which is kind of another nice opportunity. And we're going to need some volunteers to do that. It's something like a field geology conference that we did before. So you'll hear from us about that. The 2018 all hands call for abstracts is going to go out the first week of April, so that's next week. And pretty much everyone should be submitting for that. Every group needs to have an oral presentation by a student, and that means also a postdoc. Okay. What we're thinking we're going to do this year for the group by group talks is take the hypothesis that you're ostensibly working on and change it into a general question, and that is what you're supposed to talk about or towards to the extent that you can. Okay? So this will all go through your advisors too, and we'll work at all that. UT has something to say about what the students are going to do for the all hands.
I believe it's for the all hands, but
I'm sorry?
I believe it's possible to get it done for all hands. I would like to get together again because to move forward what we have done last year, posters, whether it's a publication or just update the poster a little bit and post it on cyber poster room. And we're going to meet and discuss potential opportunities to move forward.
So you'll hear more from Eugene.
Eugene's got a meeting scheduled. Yeah. Monday, 11 to 12.
This coming Monday, 11 to 12. So we asked her to get the students to talk about what they'd like to do based on what they did last year. We thought that was a big success, and we thought, you know, either you can do something different or you can move it forward or something, but you guys can talk about that. Other comments on it? The next seminar is April 23. It will be our time to get together and talk about field plans and data protocols. That's kind of an organizational thing. That's at noon, April 23 at noon. And then we have an opportunity. We are hosting this geophysical workshop. Yeah. I don't know if you know about this, man. You probably don't know about it. And Jennifer, can you guys talk and make sure that Jennifer, you know how to get her on the email and that she knows how to just do it?
We're still planning, but I'll get you.
It's run by Rutgers, so they're gonna be here. You guys know a little bit about them. Anyway, they wanna make t-shirts and they wanna know what is our logo.
It's not that one.
Oh, I
It's
missed it.
Natalie. We're gonna make t-shirts
Natalie.
to incentivize people to help us.
Oh,
we need a-
okay, I didn't realize, I'm sorry, okay, that's.
And everyone that helps gets
Well, why don't you
t-shirts.
make it for the work for the geophysical field again?
We can.
Yeah. Great idea, okay. The problem is we have no logo, that's the problem. So we need some creative person to help us come up with a logo for this t-shirt. It doesn't have to be our official CZO logo, but it needs to be something that's Shale Hill CZO. So Natalie, do you want to say any more about that?
No, that's perfect. So, yeah, if you have any ideas, I was gonna mock something up too, but we can, if you have a
Oh,
good
I see.
idea, I'll give you a shirt. You can have, yeah, and if you help us, you can get an extra shirt.
Natalie, what is your email?
It is NZA, I don't know where the Z came from. So, NZA 216.
Okay, NZA 216, Natalie. And so she's gonna be helping us read this big, high-density seismic thing in Shale Hills, and she wants to make those, or a t-shirt, but we need something creative on it. That she's either gonna come up with, but maybe there's somebody that would wanna facilitate that, okay? Any other comments? Okay, well, you know, we were going to talk about this with Sarah Ivory, but I guess Sarah.
Yeah, I
couldn't
guess,
participate. So some
I
of
think
the
she's
whole
busy
reason.
today, she's a visitor or something, so I have some slides that I'm gonna put on, like Sarah had.
Okay, all right, so that was kind of the impetus for this conversation, because Sarah Ivory is going to join geosciences, and she's been working with Roman on this topic that he'll tell you about, and she's still at Ohio State as a postdoc. She's gonna Zoom, she's gonna come here, and she's gonna Zoom, but apparently it's not working, so we just hand it
Not
over.
working because
Because she couldn't come at the last one. So I don't know, Jennifer, what do you know?
What I know is she was never available to come and Zoom thing, she got a conflict.
She was going to do a Zoom, and then at the last minute, now it's
Oh,
not.
let's see it.
I think it was probably just a misunderstanding, I think, in terms of what the level of participation was. I'm not
How
quite
could there been, this has been planned for so long? Okay, well, whatever, we'll figure it out.
All right, so I'll try to keep this short-ish, so we should be able to get out of here at 4:30. But what I wanted to do is give a brief summary of some of the stuff that we've been doing in Garner Run as a sort of backdrop to new work that we're starting in Bear Meadows, which is a site that's not too far from CZO. It's outside of Shavers Creek, but it's nearby. So some of this will probably be familiar. Some of it will be refined and updated. So some of it is pulled from, so Joe Marie has a paper that's in press right now at GSA Bulletin. So that will be out, probably in the next 6 months or so. All right, this is mainly work with Joe Marie, but also with Al Den, who's a master's student with Paul Bierman, and then some input from Sarah Ivory, and then there's a bunch of folks involved with the geophysics that I'll be presenting some new work from that also.
Should be the right button.
And just to make sure you know, our CZO has 3 sub-catchment fee study. The place that you're gonna work is Shale Hills. This is one of the other ones. You're gonna wonder why he's not talking about Shale.
Okay, so for context, here we are in State College, right where the laser pointer is. Shavers Creek, which encompasses the current iteration of the CZO, is outlined in teal. And then in different colors here are different glacial advances throughout the Pleistocene in Pennsylvania. Okay, So we're sitting in an area that was never covered by ice, but it came close. So we're subject to, throughout the Quaternary, cold periods and warm periods that were associated with the advance and retreat of the Laurentide ice sheet about 100 kilometers to our northeast. All right, so the main questions motivating our work here is we want to understand what the legacy of the Pleistocene periglacial processes is that is preserved in the regolith and colluvium in this landscape, and then what is the impact of this legacy on the form and function of the modern critical zone. Right? We can get a first order impression of this imprint by looking at things that are visible in the topography. So this is from LiDAR surface topography at a resolution of about 1 meter per pixel. And in this image, you're seeing features that we interpret as solid fluxion lobes. So these are characteristic of periglacial surface processes that require cold temperatures to sustain permafrost in the landscape. And then we have features like this, which are landslides that are not, that can't be ascribed to the current climate environment. So the only way you get these sort of slope failures on really low angle slopes in this part of the world is by having sort of a collapsing permafrost. So we know that these are relic features that are still preserved in the landscape today. So we have an indication that these landscapes have were altered heavily by periglacial processes throughout the Pleistocene, but not much has happened since. These are preserved really well today. We can see them, they're really crisp in the landscape. So we have a first order observation that stuff was happening during cold periods or maybe transitional periods, and then it's not happening very fast today. All right, so to sort of set up, to zoom in on where we're going to be looking at today, this is the Shavers Creek watershed. So if you're unfamiliar with this landscape, so north is, I've kind of rotated the whole watershed. So I think north is now what, that way or something. But there's 3 focus sites that we've been working on within CZO. The Shale Hills site is the blue star here. The Garner Run site, which is the next one that we sort of expanded to, is the red star, and the watershed is outlined in black. And then the coal farm site, which I'm not going to be talking about today, is in the yellow here. The key thing I want to highlight here is the contrast in erosion rates that we have inferred from cosmogenic nuclide data from Garner Run versus Shale Hills, to just emphasize that Shale Hills is eroding at about 4 times, 3 to 4 times faster than Garner Run. So we have this sort of backdrop of the rate that the landscape is eroding controls the timescales of the residence times and timescales of adjustment to large-scale perturbations. So we're going to be looking primarily at Garner Run here, where we have slow erosion rates. There's a thick colluvium that integrates, as a consequence of the slow erosion rates, multiple climate cycles. And we're going to probe into looking at the timing of that. And then later in the talk, I'm going to look to our new site, where we think we have maybe even longer record preserved to look at sort of this integrated history of critical zone processing. Okay, so Garner Run, we take a cross-section of the geology here. So this is a block diagram showing Garner Run sitting within this valley. It's a structural valley. So we have dip slopes of sandstone on either side of the catchment. And in the center of the valley, we have this low sloping bench that is characterized by this solid fluxion lobes in the surface topography that we are inferring is an accumulation of material from hillslope delivery of during periglacial times into the valley floor. This material that's being delivered into the valley floor is coarse grain and big enough so that when it gets into the valley floor, it's hard to evacuate by stream processes. The grain size of these sandstones is big enough that once it gets into the valley floor, it sticks around for a long time. So we have these sediment traps that are good traps for preserving material to accumulate over long time scales in a landscape that we typically don't find long-lived sedimentary deposits. Most of the time, we think about sedimentary deposits as being in depositional areas, coastal regions or offshore. In this case, we have a headwater catchment that's preserving material partly because of the grain size of the material being delivered, and also these sort of big deviations from steady state by having climate going cold and warm and cold and warm. All right, so quick tour through our data from cosmogenic nuclide analysis at Garner Run. So we measured a number of samples at the surface. So these consist of stream sediment in blue, soil samples from the groundhog pits. So these are the 3 or 4 groundhog pits at Garner Run, and then boulder chips from surface material along from boulder fields to the surface. And each of these samples, we measured the concentration of beryllium-10, which is a nuclide that's only produced from interaction with the sort of upper few meters of the Earth's surface. And so the concentration of beryllium-10 in the sample can tell you something about how long it's been sitting at the surface. Or you can invert it to think about an erosion rate. The concentration of all this material is sort of similar to each other, so we have a consistent story, whether we're looking at stream sediment, soils, or boulder chips. And this corresponds to time scale or erosion rates of about 7 meters per million years lowering that integrates over 40 to 140,000 years. So already we have an indication that the stuff is sitting at the surface or within the upper meter of the Earth's surface over timescales that are longer than the glacial interglacial timescales in the Quaternary. So the second thing we wanted to do with this is try to understand the timescale of fill accumulation in the valley fill. And the way that we did this was we had 2 approaches. One is we could estimate the volume of fill that's in the valley axis, and then use this erosion rate to back out sort of the minimum time scale of accumulation, assuming that none of that material is leaving the catchment. Okay? And so if we do that, we can estimate the volume just based on the geometry of the topography, and we can divide that by the area that's on the hill slopes and then the erosion rate to get a time scale that is 300 plus or minus 150,000 years. So there's pretty big error bars on this, but it gives us a sort of minimum time scale of accumulation in the valley axis. The second approach we use is to use multiple nuclides, so multiple cosmogenic nuclides from the same samples extracted from a 9-meter core into the valley fill. So this is the HV1 core from Garner Run, and we measured beryllium-10 and aluminum-26, which are nuclides that are produced at a known ratio. So they're produced at a known ratio at the surface, but they have different half-lives, and so they decay at different rates. And you can use the ratio of aluminum and beryllium to say something about how long that material has been shielded from surface production. The story from this is that we have timescales that have to be a minimum timescale of 340 plus or minus 80,000 years of accumulation for the upper 6 meters of the core. Okay, so the lowest sample that we had from this core was 6 meters down, and so we can constrain the timing of that upper 6 meters of deposition. Okay. So these are, broadly in agreement. They wouldn't necessarily expect them to match up perfectly, but they should both, we should be able to satisfy both of these constraints. So that work that I just showed, so that all comes from a paper from Domery that we're sort of, it's in press and out the door. The key conclusions from that initial work at Garner Run is that these structural traps, so these synclinal valleys, the slow erosion rates, the lithology of coarse-grained sandstones that deliver armor material that's hard to evacuate from channels, this leads to these areas that preserve long-lived records of Pleistocene climate controls on hillslope processes. What I mean by this is we have a local record, a local depositional record that we can interrogate to learn something about how climate change throughout the Quaternary influence the delivery of sediment off of the hill slopes. This is a rare opportunity to dig into the feedbacks at this sort of granular scale like this. And then the second thing to note from this work is that the modern critical zone in these landscapes is a relic of past processes. Okay, so we need to take into account the geologic history when interpreting our models. The key take home is that these landscapes are not at steady state. Right? They're recovering from these perturbations over a variety of timescales. The next steps, and what I'll focus on a couple of these in the remainder of my time, is we want to understand how we can predict the spatial patterns of these influences. And so where we don't have cores that constrain the thickness of these fills, can we use geophysics to expand our understanding of subsurface architecture? The second question would be how do the climate perturbations in the Quaternary compare to other perturbations like midpoints over geologic timescales or anthropogenic perturbations in legacy sediments of hundreds of years of intense land use in this area. So I'm not going to talk too much about this. This is stuff that Perry in particular is starting to work on at Cole Farm. And then the third topic here is the work that we're just getting started at Bear Meadows with Sarah Ivory, is to try to see if we can constrain the local terrestrial paleoclimate and paleoecology from these records. So right now, so far, we've just been focusing on the record of erosion and burial that's recorded in the quartz, and we want to see if we can find organic material that we can use to reconstruct, find proxies for paleoecology or paleoclimate. All right. So this is now the next part of the talk. What I want to walk through is sort of insights that we've gathered from shallow geophysics at Garner Run. And some of this I've presented before, but we're just in sort of the finishing stages of trying to get this written up and out the door. So we have some new interpretations and visualizations that I wanted to highlight that I think some of you will find interesting. So this is work that's been done with a number of people both at Penn State and outside of Penn State, including Xavier Comas, Greg Mount, Jordan Hayes, Lee Guo, Henry Lin, Fardoon, Zarif, Brandon, and Sue. So this was, a lot of the data was collected, I think, 2 summers ago already, and I'm going to be presenting some of the synthesis from that here. So just as for context, Garner Run, the catchment of Garner Run is sitting right here. State College is to the northwest, and there's a couple different transects I'm going to be focusing on. The first one I'm going to walk through is at Joe Hayes Vista. So this is an area where the highway goes over Tussey Mountain, and we have an exposure and a road cut that helps us give us some constraints in what's in the subsurface. Okay? And then the other two are both within the Garner Run catchment. We have one transect that spans from Tussey Mountain to Leading Ridge along the Groundhog soil pit transect. So here's a spot where we have multiple geophysical methods as well as soil pits dug at 4 spots along this transect. And then I'm going to show some data from a shorter transect that goes across that HE1 well. So this is a spot where we have the 9-meter well that gives us some constraint on what's in the subsurface there. All right, so this is some data from Joe Hayes Vista. It's a little bit tricky to see this upper picture because I wanted to scale it at the same scale as a geophysics survey. So all 3 of these images are at the same scale. This is an image that is stitched together from pictures along the road cut along Highway 26. And you can map in detail this interface between the colluvium. So this is material that has been mobilized and sort of consists of like boulders and soils. This is like a periglacial colluvium that's overlying in place but fractured bedrock. This is what you can see at the surface, and it's easy to map this interface in the imagery. From looking at this image and mapping, there's about 4 meters thick of colluvium sitting right on the ridgeline. So it's a pretty thick interface, even though we're up on the ridgeline of Tussey Mountain. The other 2 surveys I'm going to show is one is from ground penetrating radar. This is actually from across the highway, but in a similar location. So this is right by the well at Joe Hayes Vista. And the things I want to highlight here is that we have a 1D velocity profile. So this is an electromagnetic velocity profile that's backed out from a common midpoint survey using GPR paddles. Okay, so this is showing the velocity, a 1-dimensional velocity profile with depth. And at 4 meters, there's a jump in velocity. It's subtle, but I'm gonna go into detail about this in the next slide a little bit. But there's an increase in velocity at about 4 meters depth that corresponds roughly with that 4-ish meters thick colluvium. And then if you look at the reflectors in the GPR, there's a switch from mostly horizontal reflectors in the upper 4 meters to some dipping reflectors below that. So there's a lot of mumbo jumbo that people that look at GPR can pull out from this that I have a hard time seeing, but there's an interface, so supposedly an interface there as well. In this image is now showing a shallow seismic survey. So this is a seismic survey from just above the road cut. So this is maybe back 50 meters from the road cut. And this is showing the pattern of P wave velocity from this shallow seismic refraction survey. We're hitting a sledgehammer with a string of geophones recording the impulses from that. Again, there's a boundary here where there's a steep increase in velocity, or the steepest increase in velocity happens around 4 or 5 meters, and the upper 4 or 5 meters is characterized by low velocity material. Okay, so we're going to use this as sort of a calibration point to think about how to interpret the geophysical data from an area where we don't have very good constraints in the subsurface. All right, so the first image I'm going to show here, this is now a cross-section from our GPR data that spans from Tussey Mountain all the way down to the valley floor and then back up to Leading Ridge. Okay, so we're looking at a full transect. This is a GPR survey that was, we dragged 2 antennas on a cable through the woods and over the boulders, and made, this was a half day of data collection. So really an efficient way of gathering a lot of data. And each of these points along here correspond to areas where we did detailed profiles to get 1-dimensional velocity profiles to help calibrate how to convert the time to depth to the other parts of for the rest of the profile. The things I want to highlight here, I've shown some of this data before, but the key thing I want to highlight is these new velocity profiles. So these velocity profiles have been cleaned up since the last time I presented this data. And what I want to highlight is these velocity profiles are color-coded by bins of velocity. So the slowest velocity material is in light blue, and we're going to interpret that as like a fine-grained soil. The higher sort of intermediate velocities, we're going to interpret that as a mix of boulders and soil. For context, right, the surface at the Joe Hayes Vista was this material with this velocity. And then below that, we have higher velocity material that we're going to interpret as fractured bedrock. What I want to focus on is these 3 surveys that were done right next to the soil pits. These are the groundhog soil pits. You can see the jump in velocity from the blues to the orange. Okay, that happens at the same spot as the depth of refusal for those soil pits. Okay, so these dashed lines are the independently measured depth of refusal. In the bottom one, right, this was jackhammered a little bit also, but this represents some boundary basically of stuff that's diggable and stuff that's not, and it lines up with what we pull out of GPR. So I think that's pretty interesting. I'm not entirely sure. On that we see less of a contrast across that depth of refusal on the Tussey Mountain mid-slope side. This might just have to do with the challenges of just digging within that boulder layer to start with. All right. The other thing I want to highlight here is there's an asymmetry between Leading Ridge, which has this low velocity layer at the surface of these blues, and then Tussey Mountain, where that's absent. Right? The note from our surface observations is also we have more boulder fields sitting on Tussey Mountain than on Leading Ridge. Right? So I don't want to go too much into more detail about that, but we have a pretty good connection between the GPR data, our surface observations, and our soil pits. The next thing I'm going to show is, this is from the seismic surveys within Garner Run. And now what I want to highlight here is something, I don't think I've shown this before, but this is now looking at a perspective view into Garner Run. Okay, so this is a LiDAR perspective where you can see that low sloping bench in the valley floor, and then the Leading Ridge and Tussey Mountain hill slopes are steeper. This is a vertical exaggeration of about 2. And you can see this is the road, this is the Garner Run road that you drive in on. HV1 well is sitting right there. For the next slide, what I'm going to do for the next couple slides is I'm going to zoom in and focus on the geometry of this low sloping valley hill, and I'm going to vertically exaggerate it by 5 times. Okay? So it's going to be a little bit, it might be a little bit disorienting at first, but I hope to show sort of the geometry of these individual lobes that you can pull out just from the LiDAR, and to think about the context between that, the location of the drill core, and the seismic data. Okay, so now we're zoomed in. Okay, so we're zoomed in just in a small patch, so that, you know, Tussey Mountain is way up here, Leading Ridge is way up here. The well, this is the HV1 well. It's 9 meters, so this is to scale here. So this is 9 meters deep, that well core. The road here looks pretty bumpy when you vertically exaggerate it by 5 times. And what I want to highlight is you can see a boundary where there's sort of this thick low material, and then there's sort of a low area that happens to be right where we drilled the well. All right, and so there's an area basically of thick colluvium that this zone right here, so this thickness is about 10 meters of additional material that's on top of the surface that we would be standing on at the HV1 well. So there's an area here where that thick colluvium is absent. Then there's 2 seismic lines that we have, and I'm just showing the partial seismic line. The groundhog one continues up the side of Leading Ridge, and then the HV1 well just goes from basically the toe of this little bit of the thicker zone over to the well itself. Right? So now what we're seeing here, so I'll walk you through this, but this is the seismic tomograms showing the velocity. This is the P wave velocity, and they're kind of tilted into perspective. The lines, so follow this line across here, follows this surface trace. Okay? And so what you can see here is there's about 10 meters thick of this low velocity zone that corresponds to the, you know, the well was drilled to 9 meters. This suggests that there's only maybe another meter or so of unconsolidated colluvium before we get into bedrock below that. As you move up the slope and you hit this toe of this material coming in from Tussey Mountain, you can see that wedge of stuff thickening against the side there. Okay, so this suggests that we're actually picking up, you know, the subsurface interpretation from the seismic lines up with what, you know, what my interpretation from just looking at the surface topography of the geometry of these drapes. If we go over to where the HV1, the groundhog seismic line is, okay, so now we're fully on top of this sort of lobe of material that I said had a relief of about an additional 10 meters on top of that surface. We see the depth of the thickness of this low velocity stuff is closer to 20 meters. Okay? So we have a pretty, a nice expression of the, what we can best infer from the LiDAR geometry of these deposits with the seismic imaging of them. All right. So we have GPR and seismic surveys that are now providing key constraints on the subsurface architecture that can be used to better understand the spatial variations in things like thickness of soil, periglacial colluvium, and fractured bedrock. Okay? So this is work we're right now we've been focusing at Garner Run, but Xavier Comas and I have a proposal that's pending right now to try to get some money to expand the scope of this project to look at how this varies across central Pennsylvania and take advantage of aspect gradients or differences in the geometry of the hill slopes themselves and the underlying structure to try to pull out sort of the climate signature of hill slope processes from that. All right, so the next thing I want to move to is we're going to go from Garner Run, which I focused on here, over to Bear Meadows, which is about 10 kilometers to the northeast. Okay? And the work at Bear Meadows, this is work I've started to do with Sarah Ivory, Joe Marie Del Vecchio, and then Paul Bierman to help with the cosmic nuclide dating. And we're going to be investigating Bear Meadows as a landscape that's similar to Garner Run, but with a couple key differences. And we're going to try to see if we can pull, we're aiming to pull a coupled record of paleoclimate, paleoecology, and hillslope erosion from a single landscape here. Okay, so why Bear Meadows? If we go to Garner Run, this is just a schematic now looking at Garner Run. You'll notice the color ramp is flipped in the seismic. I apologize for that. But there's this low sloping valley floor that we showed was these periglacial colluvium accumulation that spans, multiple glacial interglacial cycles. And so this is material that is older than 300,000 years, and it highlights this long-lived record of Pleistocene surface processes that is preserved in a headwater valley. The problem, though, is that there's no organic material recovered from the core, so it makes it hard to pull out a paleoclimate history from the same material. The reasons for this are twofold, probably. Primarily, it's not an ideal setting for preservation. So Garner Run is well drained. It has oxidizing conditions in the subsurface, so it's not very good for organic material to be sticking around for very long. And then on top of that, the sampling from the drill core was not sampled with the express intent of trying to go after that fine-grained organic material. So what we're going to do is we're moving to Bear Meadows, which is in a similar setting, except that it's in a closed basin. And so we're in a closed basin that has been a peat bog, at least from the Holocene to present. So we know we have organic material going back 10,000 years. So there's pollen records that were published in the 60s from sort of the top 5 or so meters of the bog out in the modern peat bog. Bear Meadows is a much better track than Garner Run. So we have a geologic setting that enables a better preservation of sediments. It's not as well drained, so there's more likelihood that we actually preserve pre-Holocene organic material. Okay, so we don't know this yet. So we got some seed money from PSIADE to do some drilling, and we're just sort of in the process of getting that started this summer. But this over spring break, we went out and did some preliminary geophysical surveys along this sort of toe slope of this ridge line to try to estimate the thickness of sediments in Bear Meadows, figure out how much it's going to cost to drill. So I'm going to zoom in and just show some hot off the press results, as in they're still very preliminary, and they represent us trying to learn how to do geophysical processing on our own. So it's going to be a little bit rough around the edges. So this is now looking sort of down slope at this toe slope. Again, this is vertically exaggerated by 5 times, okay, just to highlight the flatness of the peat bog. There's this toe slope of bouldery colluvium that's similar to the material that's preserved in Garner Run. And then up above, there's steeper hill slopes that continue up to the ridge line. This road right here is the access road from the Bear Meadows parking lot. And we went in March and braved the snow to take a seismic line, about 200 meters of seismic line, right down this toe slope. And so we did that with Sridhar Nandakrishnan here at Penn State, and then Greg Mound at IUP. This summer, we have planned out some exploratory drill cores to try to establish the subsurface stratigraphy and collect some preliminary observations of whether or not we have organic material, what's preserved, what we can do with it. And then in this fall, we're planning to put together an integrated Earth systems proposal to NSF to try to get money for the actual sample analysis. The detailed analysis of the samples in the cores is a whole nother ballgame in terms of cost. But first, we need to figure out what material we have available to us. Our goal here, right, is to get down to pre-Holocene peat bog deposits. And that, depending on what the stratigraphy here, those peat bogs could have been in greater or lesser extent than the modern peat bog. But it's hard to drill in a bog here. So we're going to start from the road and see what we can get. Here's just this preliminary seismic data. The velocity profiles are similar in color scale as the previous figures I've shown. There's a little bit of a problem with the connection here to get these things stitched together. But in general, there's 30-ish meters of alluvium on the uphill side and 10 to 20 meters of alluvium on the downhill side. Right? So this matches what we would expect if this is kind of just a wedge sediment sitting on top of a different material. There's a lot of details here that I don't want to say anything too much until we have actually completely processed the data. All right, so this then brings us to what we're going to be doing with Sarah. So just like I'm going to put on my Sarah Ivory hat and sort of give a brief introduction to the type of stuff that she does and sort of what her background is, and then how we're going to try to slot that into the study at Bear Meadows. So she's a postdoc right now at Ohio State. Her background is really in using pollen records, so fossil pollen records in big lakes in Africa to look at paleoclimate and paleoecology shifts throughout the sort of Pliocene to present. Right? And these are a couple slides from Sarah, sort of looking at these transitions that switching from sort of human to dry periods in Africa. You can think of this as there's a similar level of change that's happening in central Pennsylvania when we shift from periglacial to temperate climates. Right? This signature should be recorded in the vegetation that's growing at the surface that leave behind biomarkers like pollen or leaf waxes or things like this that we might be able to find preserved in sedimentary record that we can use as a proxy for paleoclimate. All right, so I'll just skip through. Okay, so this is sort of her bag is really looking at connecting paleoecology, paleoclimatology, and sedimentology together. And one example of this is to kind of figure out how we can pair together proxies that are pulled from a sedimentary record. In this case, it's peat cores from lakes. For Bear Meadows, it's going to be a tens of meter core from colluvium, so it's a little bit of a different environment, but it should be fun to explore. So I don't think we'd get one of these guys into Bear Meadows, but I think maybe maybe in the future. All right, so some of these examples are things like fossil pollen, biomarkers from leaf waxes, archaea, that's kind of crazy. Charcoal from fire, right? So you can look at periods of enhanced fire, clay mineralogy to tell you something about weathering, sedimentation rates, right? We're going to be getting this in Bear Meadows from looking at beryllium and aluminum, the paired isotope records from the core. And then that allows you to sort of put together these series of proxy records and use these to pull out information about how landscapes have changed over time. And in particular, we're interested at Bear Meadows to try to pair together the erosional history. We've got a little viewpoint into a Garner Run, but try to get a better resolved erosional history of Garner Run at Bear Meadows, and try to pair that with proxy records to get combined with paleoclimate, paleoecology, and paleoerosion. So this, I think, would be a pretty powerful record. I don't think there's anywhere that has this type of scale of a local source to sink system that spans, potentially 500,000 years. So I think it's still high risk in terms of finding the material that we want to find, but the reward, I think, is also high. All right. So yeah, so our goal then, if we go back to this image at Bear Meadows, the idea is that we have this in the valley floor here. So the modern peat bog is an organic material that's deposited and preserved. We know at least for the last 10,000 years. We know from walking along here, right? These are the same sort of coarse-grained periglacial deposits that we see in Garner Run, and it's likely that the erosion rates are similar here to Garner Run. The lithology is similar, and it's likely the timescales are similar or longer in terms of what's preserved here. So we know we have a long-lived inorganic record of quartz to where we can pull out the paleoerosion history, depositional history from. The key is going to be seeing if we can find pre-Holocene organic material interfingered between these deposits in the subsurface. Okay, so that's sort of our target right now. So right now we're trying to drill at a few spots along this road to see if we can poke down deep enough to hit one of these features if they exist. So I think I'll leave it there. If people have questions, I think we have a few minutes, 13 minutes left.
Before you got here, we announced that we're in a speed version. Is there anybody listening? Is it Greg Mountain? Is he on?
Greg, yes.
Yes. Then we have to pass this in. Is there a question? Isn't it ecologist when I ask what a GPR is?
So you're sure?
It's on you when you're
Did I turn it on?
It's on now. You're showing seismic records down a lot deeper than what you're interpreting. Do you believe the seismic velocities at the bottom?
So I believe I think these velocities are resolved. I think that for our interest right now is mainly in thinking about the upper layer. The deeper velocity structure, if I go back to the.
Try it now. That should work now.
There's the deeper structure. I think it's interesting there. It's hard to say what we can pull from it though, because yeah. So I'll show right here, right? This contrast between what the subsurface looks like here and here. I don't know. I mean, this is a shorter line, so it's not getting as deep. So I don't know if we went deeper that we're going to see the same sort of high velocity material here. This is right near sort of the saddle in it's a drainage divide in one of these long linear valleys. I honestly, it's hard to distinguish what is even going to be underneath there, because I think it could be fractured sandstone, but it could also be, there's a shale layer that overlies the sandstone here, and I think it's tricky to resolve whether or not you're looking at shale that's pretty intact or a sandstone that's really fractured. So it's a little bit, it's tricky to make an interpretation without having any constraint on the subsurface there. But I think for the upper part, we have a pretty good handle from other overlapping methods to interpret that.
What do you expect to find when you go deeper in Bear Meadows or further back in time?
Yeah, so that's a good question. So I think this gives us a view of kind of what our initial hypothesis is in terms of what we expect to find. Is that I think we'll probably see deposits of varying ages. So the deposit that we find at Garner Run, we have a layering within that core right? And the ages of that core, there's an abrupt break that requires multiple pulses of deposition. So I think because we're looking over multiple glacial interglacial cycles, it's likely that we're going to see an interfingering or a competition between sort of the bog formation during warm periods and periglacial sediment flux from cold periods. And so it's unclear how well that stuff is preserved as you make the transition from one climate to another. So I don't know whether or not we have a partial record of how long it spans, how many of these were missing or preserved. But I suspect that we're going to find at a minimum this coarse grain stuff that's delivered from the side slopes. Maybe, hopefully, some interfingered organic material, even if it's not like a thick bog deposit, some better preservation of organics because of I suspect that we're going to be in a more reduced environment in Bear Meadows than in Garner Run. And then eventually, there's going to be a bedrock underneath that. And I don't know what that bedrock interface. It's hard to say what that bedrock interface is going to look like. But probably not more than sort of 30 or 40 meters deep. That would be my guess, based on the sort of the high velocities below that we have in some of our profiles. Yeah.
So going back to the original premise, how much do you think the working with Sarah and getting the bare metal information will help us better understand the present day critical results?
Yeah, so I think for Bear Meadows, I think it becomes a link is I think more tenuous for the Bear Meadows study, which is really a paleo study. It'll help us understand how sensitive periglacial landscapes are to changing climate, so we can get a sense of the magnitude of what the swings are in terms of sediment delivery from cold to warm periods that you might be able to extrapolate to places that are undergoing warming today. I think that's what I meant more by that statement early on was from trying to use the geophysics to better understand sort of the spatial variations in that sediment cover, right? So right now, I think it's hard for us to sort of a priori go out here and say, there's 20 meters of colluvium here that you need to put into your hydrology model. And to where that bedrock interface is, how the fractured bedrock and intact bedrock interface varies, I think that's, in general, is really poorly known. And so what we're hoping to do with the sort of more extensive shallow geophysical surveys, both the GPR and the seismic, is to try to just collect the data so that we can start to sit back and see, are there patterns to the subsurface that we can infer from things that we can measure more readily, like from the LiDAR data or from surface mapping of surface cover that we might be able to get from satellite imagery, some way of trying to get a window into that subsurface environment. I think right now it's just like it's a black box, and every time we do a survey, we sort of find something new and exciting. So trying to just get a baseline data set to start looking at that in more systematic detail.
I mean, there's also something to be said though about like what the pollen preserved in a site tells you about the climate conditions at that moment that the material is being deposited. So previous studies have obviously looked at sort of the succession of vegetation as you either warm up or cool down, and we can gain insight into whether there is more or less sediment moving in the system given a specific vegetative assemblage or something like that. And that can tell you something about how plants back in the day were affecting physical and chemical weathering versus, plants at a different climate, or when there were no plants because it was tundra, something like that. That's what I'm hopeful for, at least. Oh yeah, or whatever happens after tundra, cold desert wasteland, whatever.
I have a question for you, which is a little bit outside of what you were talking about, but I've talked to you about this before because I'm interested in the saddle point in Garner Run. Can you just talk about that and put it into geomorphological context for people? Because one side of it should be winning over time.
Yeah.
And what do we know about that? And what do you think about that? And explain it, because I don't know if people follow it.
All right, so it's probably easiest to see in this image. Okay, so Garner Run is sitting here. There's
We can't
there's
really
a
see.
drainage divide.
Thank you.
What's that?
They
We're
couldn't
blocking
see
our
it,
Okay,
they're
sorry.
blocking.
So there's a drainage divide in Garner Run here, that everything to this side flows out Garner Run and into Shavers Creek. Everything to the northeast flows out this side and takes a different path, right? And so I think what Sue's asking is how stable is this position in the landscape, and whether or not, and is this changing over time?
And that's called what again?
It's a saddle, right? It goes up on
Oh,
either
saddle.
side, but it's a local high. If you've ever noticed when you drive it up, there's Valley roads up here that goes up, then it goes down ever so slightly. And we're sort of in the top of our watershed is essentially the saddle point. It's a very unusual thing. It's not totally uncommon, but it's kind of unusual. And it's interesting because one stream is trying to, that's what he's gonna explain right now, I think.
Yeah, so right, this is a really subtle divide here that is a consequence of the fact that these are these long, structurally controlled valleys, right? That this sort of lineaments like this are controlled by the underlying fold geometry that was set up in Paleozoic by Paleozoic tectonics, right? And so I think at Garner Run, I suspect that divide is pinned kind of to one of these structural highs also. And so you see, like, this is this ridge right here, right? The bleeding ridge. You can follow it. It's not all the ridges are just like a perfect accordion, two-dimensional accordion, but there's plunging folds and things in here also. And so I suspect that part of this might be related to, where you have sort of the underlying structures are kind of setting up those that sort of catchment geometry. I don't know. I think it's hard to say how, which side is winning, because there might be some longer term winning or losing that's overprinted by the short term periglacial processes. That the fact that you might have longer hill slopes over here that are dumping more material and might be insulating Garner Run from going back farther. I don't know.
Normally that saddle would move with time, one way or the other. One stream would win. You know what I mean by winning?
So there's some
It's a metastable feature. It's got to go away over time. But
yeah. So there's some work that's been done to try to pull out these metrics of divide stability in landscapes, and the underlying theory behind them all relies on uniform lithology in the landscape. Right?
just like everything stays safe.
Exactly. And so
Uniform
the
stays
framework
safe.
for
That's all
that, when you take that framework and you try to apply it here, you're going to get something that doesn't make any sense because you have such a strong lithologic and structural imprint on the landscape. So it's not as straight. It becomes then not as straightforward to kind of pull out just like a simple metric of whether or not one side is winning or not. You can take the simplest approach is just to look at the slopes on either side, and they're not that different. So if any, it's very tricky because the slopes are low enough that the factors like these sort of big lumps of material coming in can totally change the efficiency on one side or another. So it's not, there's no, I think, general interpretation that pops out.
Okay, we wanted to finish early just because of the family weekend or whatever. So thank you very much. And I'm sorry we couldn't get Sarah. And everybody should be thinking about their abstracts for all hands. We're done, so we can start putting out everything. But for the all hands,